Hello everyone, my name is Sophia Abraham and I'm a PhD student at the University of Notre Dame. And in this video, I am delighted to present our paper, Adaptive Autonomy in Human-on-the-Loop Vision-Based Robotic Systems, where we propose our solution based on adaptive autonomy levels where a system can detect a loss of reliability within an operating context and temporarily lower its autonomy levels while increasing human engagement in decision-making processes. Computer vision algorithms are often utilized within everyday autonomous systems, including driving systems, factory floor robots, and small unmanned aerial systems for emergency response missions. And while computer vision proves to be an asset in many of these applications for providing information and supporting autonomous decision-making, they are not completely reliable, which can result in poor autonomous decisions. One notable example of this is Uber's self-driving car accident on March 19, 2018, resulting in the fatality of a woman whilst the vehicle was in autonomous mode with a human driver as backup. The vision system detected and classified the woman 6 seconds prior to the crash as an unknown object, then as a vehicle, and finally as a bicycle. And although the system recognized the need for emergency braking 1.3 seconds prior to the impact, it was too late to avoid the fatal collision. Postmortem analysis actually revealed factors such as dark clothing on the pedestrian and low roadway lighting contributed to this accident. And though there are many causes of computer vision failures, many can be attributed to the biases introduced when training the models, including imbalanced data where classes are not represented equally, as well as racial and gender biases. For human-on-the-loop systems, where systems are enabled to act autonomously and humans serve a supervisory role, it is critical for a human supervisor to understand whether the vision model can reliably react autonomously in an operating environment or if further human intervention is required. Take, for example, a small unmanned aerial vehicle detects a potential victim in the water, streams video of the event, and requests further input from a human operator. The system can be designed to utilize varying degrees of autonomy when a victim is detected. In the case of 43% confidence, as shown here for the detection, the system can either 1, ask the operator what action to take, 2, automatically track the victim if the confidence exceeds a preset threshold and notify the operator of this action, or 3, understand the reliability of the model within this context to decide whether tracking is appropriate, such as if the model is well trained on examples containing snowfall. The third option represents adaptive autonomy, where the small unmanned aerial vehicles operate autonomously when the models are equipped to perform in the operating context and engages the operator when the model is unreliable. In order to design a human-on-the-loop system with computer vision-related adaptive autonomy, we considered 3 questions. 1, when and where do the agents exhibit autonomous decision-making behavior? 2, under normal operating conditions, what decisions should the agent be able to make autonomously? And 3, how is the autonomy suppressed or increased at this interaction point? These questions also help guide the specification of system-level requirements throughout our approach. And since these decisions are based in computer vision model predictions, how can we ensure that these predictions can be trusted? The model is trained on a specific data set, which can introduce bias into the vision-based decision-making. We dive into 2 separate methods to estimate the reliability of the vision model for a given task, which include 1, evaluating the uncertainty of the model caused by the acquisition sensor and the model parameters, and 2, performing covariate analysis to determine whether the attributes in the training data reflect the conditions in the operating context. Our described approach thus seeks to estimate the uncertainty and reliability of the vision model for a task. For example, trying to detect people who are drowning by utilizing these 2 methods, and then using the context of the operating environment, such as knowing that the drowned victim is a light-skinned female who was drunk and fell into the river, and in the event of low reliability, the system is then able to appropriately lower its autonomy levels and engage the human operator. To illustrate the applicability of our approach, examples will be drawn from our very own human-on-the-loop drone response system, which deploys multiple small unmanned aerial vehicles to support time-critical emergency response mission. Now let's begin with evaluating uncertainty. Uncertainty refers to observation incompleteness, which can arise from the model and data noise. We adopt state-of-the-art techniques such as that of Autonomy, where Bayesian belief networks are combined with Monte Carlo sampling to estimate data and model uncertainty. The data noise uncertainty is extracted by taking and propagating the input uncertainty corresponding to known sensor characteristics V, like that of a camera, which is assumed to follow a Gaussian distribution and can be acquired from system identification or hardware specification to obtain an output uncertainty resulting from the noise. For our drone response system, these factors can include glare and excessive vibration caused by the system or camera mount. Uncertainty of the model is estimated with Monte Carlo sampling, which is a random sampling method of the parameters of the model with test time dropout to use an ensemble of T-networks to capture the sum of the variance among predictions to estimate model uncertainty. The total uncertainty is then the sum of the variance of the propagated input uncertainty and average data variance collected over the Monte Carlo samples. In other words, it is just the extent by which the estimation of the uncertainty changes between each layer of the computer vision model, induced by both the sensor noise and model parameters. This technique can then be integrated with the streaming confidence, representing the uncertainty estimates from both the camera and vision model that transforms video streams into semantic data representing confidence intervals, where confident requires no intervention, uncertain requires possible intervention, and no confidence requires intervention. These intervals are tuned empirically with field data and intervention budgets, which would include safety factors, event occurrence, and human factors for our drone response system. In addition to estimating uncertainty, our solution considers whether the current operating context is ill-matched to the model's training data through covariate analysis. Covariates refer to the known measured attributes within the data, and a phenomenon known as covariate shift occurs when the training data differs from the data seen at prediction, which leads to incorrect predictions at a high confidence. Take, for example, a model trained on data with only examples of clear visibility conditions may perform poorly when deployed in low visibility. To mitigate this issue, we proposed the formation of a generative model based on the work of Mel McCurry and team to capture the distribution between multiple continuous covariates and model performance to inform the decision-making process. As a high-level overview, the generative model is formulated by annotating the data, estimating pairwise similarities, and then performing the density regression. For reference, let's take a person detection model, which is pertinent to our drone response system. To annotate the data, a dataset containing n images must be annotated with the relevant covariates. This could include age, gender, weather, among many others. And while naturally occurring covariates like age and race may need to be manually annotated, covariates like weather and terrain characteristics can be automatically tagged through attribute classifiers. As a proof of concept, we generated 2 attribute classifiers for weather and terrain characteristics. For weather characteristics, we created an ensemble of binary support vector machines trained to classify pertinent attributes like light conditions, rain, snow, fog, as seen here, where a video stream is classified with relevant weather attributes, and utilize a popular semantic segmentation algorithm called DeepLab to tag the setting with pertinent terrain characteristics, as seen here from a sample video for the river rescue scenario, where pixels corresponding to river and people are semantically encoded on the right. Now, to capture the relationship between multiple continuous covariates and predictive performance, pairwise distance comparisons are computed between the feature sets for each image against the entire data set of n images, resulting in n squared points to produce a vector of all the attributes and its interactions, one of which is the match attribute. If the identity of the images match, meaning they are of the same image. Take, for example, the covariate of scale. Each image would be tagged with its identity and tagged attribute, and the distance between the extracted features for that image would be computed against all the other images in the data set. Finally, The full density of the general distribution of predictive scores over the continuous covariates are estimated by calculating the conditional true positive rate, which is the percentage of actual positive which are correctly identified. For example, correctly identifying people at a given false positive rate for a precondition x, which is the vector of covariates based on the cumulative distributive function of the match and non-match feature distances. With this generative model, pertinent covariates can be extracted from the operating context and run against the model to estimate the reliability of its predictive capabilities in the mission context and determine whether the system can make autonomous decisions or human intervention is required. With this computer vision-driven solution, accompanied with an awareness of the model's reliability, we can specify requirements and design a system that is capable of adapting its own autonomous behavior according to its perceived reliability. We thus identify human and small unmanned aerial vehicles interaction points by building off our existing model, which is depicted here, for human on-the-loop interaction in multi-agent mission. In addition to modeling the interactions between humans and small unmanned system, the model includes the probing questions introduced earlier, designed to aid in the discovery and specification of autonomy requirements, which for computer vision-related autonomy again includes: 1, when and where do the agents exhibit autonomous decision-making behavior? 2, under normal operating conditions, what decisions should the agent be able to make autonomously? And 3, how is the autonomy suppressed or increased at this interaction point? We focus on design-level requirements for transitioning between autonomous behavior and human intervention. To err on the side of caution, the operator is engaged in the decision-making process whenever the loss of reliability of the computer vision model exceeds a predefined threshold, or when the covariate analysis indicates that the computer vision model training data provides insufficient coverage of the current operating environment. We utilize internal thresholds to define loss of reliability as true when the uncertainty exceeds a threshold or the covariate analysis returns a score below the covariate coverage. To specify requirements for autonomy adaptation, we apply the 3 questions to our introduced example. For Q1, when the small unmanned aerial system detects a victim, it determines what actions are appropriate. For example, when a victim is detected with a medium level of confidence and low uncertainty, confirmation from a human operator is requested before raising an alert that a victim is found, aborting the search mission, and transitioning into tracking mode. The human operator can either confirm, reject, or request further imagery. For question 2, we specify 3 autonomy requirements. First, when the computer vision model identifies a candidate victim in the river with a confidence score greater than the detection threshold and a loss of reliability is tagged as false, the system autonomously transitions into tracking mode and notifies the operator. When the computer vision model identifies a candidate victim with a confidence score greater than the detection threshold and the loss of reliability is tagged as true, the system temporarily reduces its autonomy level and raises a high priority alert requesting permission from the operator to transition into tracking mode. When the model identifies a candidate victim with a river where the confidence score lies between the alert threshold and the detection threshold, then the system raises a low priority alert and continues with its current tracking task. In our example, where a victim is detected in the river, although detection threshold is 0.4, if loss of reliability is true due to the presence of snow and a lack of proper representation of snow in the training data, requirement AR2 is activated and the human is alerted about the potential victim sighting and engaged in the decision-making process, where more imagery can be requested or reject the sighting, and the system continues its search. For question 3, instead of limiting the autonomy of the small unmanned aerial system, the system uses its self-awareness to temporarily override its own autonomy and request aid from the operator when loss of reliability is detected. While experimental analysis of thresholds and full integration of the approach within our drone response system is left for future work, we included exploration of open challenges necessary to consider with the computer vision models themselves and their safe and reliable adoption within autonomous systems deployed in potentially unknown environments. These challenges include discovering and assessing salient covariates, 2, extracting attributes from image data, 3, capturing the real-time context at runtime, 4, safety assurance of computer vision-driven systems, and 5, human-machine interaction. Potential solutions and means of addressing these challenges have been included in the paper. Thus concludes our approach for an adaptive informal framework for the reliable deployment of computer vision models in the decision-making of autonomous systems. I thank you for your time and attention, and I'm happy to take any questions. Thank you. Have been included in the.
Okay, we are live now. Thank you so much, Sophia, for the interesting presentation, a very lively presentation. You have one question from the audience from Lionel Rian. It says, thank you, Sophia, for an excellent presentation. The following paper by Antonella is on a related topic, fail-safe execution of deep learning-based systems through uncertainty monitoring. Can you clarify, if possible, the differences in objectives and solutions?
Yeah, this is a great question. I briefly just looked at the paper, and so I didn't really have a chance to go through it. So I can't speak specifically on what are the differences just yet. In general, it actually looks like a great paper, so I'm happy to reference it and see it. But if you wanted to discuss it after I had a chance to read it, then I'm happy to give my email to discuss as well.
You have homework now.
I do have homework. Exciting.
Okay, Sophia, I have a question for you. So can you give me a little bit more detail on how you calculate the boundaries for the confidence intervals? Like how do you decide the three? See, this is what happens when you don't watch the three sections. How do you calculate those confidence intervals?
So we were going to do empirical testing to be able to determine the confidence intervals for our specific use scenarios, right? So for example, if we're trying to do river rescue, then we would establish the confidence intervals based on the data that we've acquired for it, and then do field testing as well to get a general sense of where those confidence intervals should be tuned.
Okay, so I think it is correct to assume that your approach works well when there's enough time for a human to provide input, correct? I mean, it would work in those scenarios. So I was just curious, like, how does your approach perform in terms of inference time, at least on the drone platform?
Inference time in regards to the detection or in the estimate?
Yeah.
Oh, okay. So it would still be real time, right? So it's supposed to act like the way that an object detection would be able to do. In correspondence with that detection, there should be an estimate with it, right? And so there was one image actually in the slide where there's a confidence meter actually on the bottom. And so it's meant to be accompanying the actual information of the detection as well. So in real time as well. And then you can go off real time to be able to tune the model to be able to behave accordingly if there's anything that's off.
Got it. So at the end, your last slide is lots of open challenges. So in your opinion, like which would be the easiest to start addressing, and which do you think is the hardest?
Out of the open challenges, let me refer to them again.
Yeah, the very last slide.
Okay, so I think honestly, one of the hardest ones to probably do is assessing what are the salient covariates. And so what the model sees as important versus what a human may see as important are very different, right? And what is machine interpretable versus what is human interpretable. And so understanding which covariates are pertinent for the machine to be able to establish with confidence what is certain of what it's seeing, I think is probably the most difficult, and making sure that we capture that in the context of the mission appropriately, I think is the most difficult challenge. As regards to what is the easiest, I would think it'd be the human-machine interaction component, to understanding like how to properly have those interaction points understood, and to be able to understand and integrate them appropriately, as into how should the warnings be assessed, and how should they be relayed to the operator, and how should that information then be integrated back into the model.
So how far along are you in the project and your vision?
On the vision side, so we have our attribute classifiers. The vision of the entire project, yeah. So we do have our attribute classifiers to be able to extract those covariates automatically for, say, terrain and weather characteristics. On top of that, we have the entire foundation. So drone response is what we're going to integrate it into, right? And so that's all been set up. We also have some what is it? We have some preliminary data from river rescue scenario with the South Bend Fire Department as well. And on top of that, a lot of these uncertainty estimators are open source. So it really just take integrating all of the pieces together and testing to be able to get those empirical confidences and then incorporate that into our model.
Okay. We have 30 seconds, so I'm going to ask you an unfair question. So you're. I learned in the backstage that you're a computer vision person. What is the hardest thing? What is the hardest thing about working with software engineers?
The hardest thing about working with I think it's me like trying to understand their world and trying to see from their perspective. From a research point, I think there's a more practical approach in software engineering, and on the vision side, there's more of an approach of trying to create new theorems in CP. But and work forward in that.